Yeah, so I'm Kate Porter. I'm a member of the Esri team at Strathclyde University, and I'm just going to give you an update on some of the activities we've been working on as part of the SuperGen core project since last year's annual assembly. And our focus for this project, at least, is improving the understanding of a range of things that are affecting the operation of tidal turbines as opposed to wave energy converters. So I'm going to talk about three topics today. Firstly, a little bit about some experimental tests that we did at the start of the summer. Then I'll move on to say a little bit about our numerical modelling work. And then I'll finish with a little bit about two different control methods that we've been investigating for power regulation when the flow speed exceeds the design condition. So we conducted 1 week of laboratory testing at INSEAN in Rome, and Tim's already spoken a little bit about this this morning because this was a joint test programme between Cardiff and Strathclyde. And Cardiff were focusing for this set of tests particularly on the effect of yaw angle and pitch offset. For our side of things, in terms of numerical modelling as well, we've been focusing on the influence of wave current flows on the turbine, and so this again was our focus for this set of tests. So just a few results to show you from the wave current tests. We've got here the thrust coefficient and power coefficient for a range of tip speed ratios. Now all of these tests on here are for a carrier speed of 1 meters per second, but then we've got with and without waves added. So what you can see when you're plotting the average values is you get pretty reasonable agreement for these. But if you then look at the standard deviation, so that's plus and minus 1 standard deviation plotted for each of the average points, you see, of course, adding a wave, you get a much bigger range in the thrust and power, as you'd expect because you've got a varying inflow. But what we're now looking into is sort of more detail about how the maximums and minimums in these fluctuating loads are then impacting things like the fatigue life of the blades and also then transferring through to different parts of the drivetrain. Another aspect of the test that we've been looking at is, and Tim again sort of mentioned this earlier, looking at how the phase of the wave relative to the position of the blade as it rotates around in the water column influences loading. So we ran two tests that were both at the same carriage speed, both with the same wave parameters and the same RPM, but the RPM was set so that a blade did one revolution in exactly the same time as one wave period. Now what we did was we ran two tests. The first one where the instrumented blade was upright as the wave crest was passing over, and then a second test where the upright blade was there when the wave trough passed over. And so what you can see is you've got a substantial difference in the maximum and minimum values, but then also through into the average values you're also getting a difference in the loading. And so this is going to be quite important in terms of understanding how the blades are going to perform. So this is ongoing work. What we're also doing at the moment is comparing the experimental results to our numerical modelling work, which is focusing on blade element momentum theory model. We're also using this work to then feed into fatigue modelling of the blades, and that's in collaboration with Newcastle University as part of the RE-CHASM project, which is a SuperGen Grand Challenge project, and Margaret Statt is going to present about that project this afternoon. And of course this work's also then feeding into further design of future experimental work as well. And just to say, we've got various papers that we're expecting to deliver within the next year or so on this work as well. So I'll move on to our numerical modelling work. So Thomas Nevalainen has been developing an unsteady blade element momentum theory model, which includes linear shear current coupled with regular waves. And he's been using this model to investigate how the variation in the loads across the rotor plane, and then how those then transfer to eccentric loads on the drive shaft. And sort of the most recent developments in this work is firstly adding random waves into the modelling, and then looking in more detail at how the loads are transferred to individual parts of the drivetrain, so specifically looking at the loads on the individual bearings. So just to demonstrate that, I've got a few animations. Yeah. So this on the left-hand side here is showing a random C state with current, and you can see the turbine operating there. Then on the right-hand side, what we're seeing is the resultant bending moment on the drive shaft. So from the contributions from the three blades. And this is then showing the magnitude and direction varying through time. And you can see there's a significant variation. And this, of course, you can imagine will probably affect the bearing life particularly. And so what Tom's been doing is he's been working in collaboration with Lloyd's Register to start to model how those loads get transferred to the drive shaft. And using a simplified FEM model, he's then firstly been able to look at the deformation of the drive shaft under the loading that I showed on the previous slide. So that's an animation there you can see. And then secondly, this model has also enabled the radial and axial loads on the three bearings of a typical drive shaft to be modelled. And you see in the plots you've also got the radial and axial loads for each bearing. The animation is the radial loads. And then what Tom's been using this for is then to feed that into a sort of preliminary bearing life prediction in order to start to see how these sort of realistic wave current loadings are impacting the bearings in the tidal turbine application. So the final part I want to talk about is two methods of power regulation. The first is overspeed power regulation. So this is when you deliberately increase the RPM of the rotor in order to increase the tip-speed ratio beyond the optimum point and hence bring the CP down the performance curve on the right-hand side. Now, one issue with this method of power regulation is that you don't want to increase the RPM too much because it's then going to cause damage to the generator. So what we want is to have a power curve that has a steep drop-off on the right-hand side, so that you only need a small increase in RPM in order to get a large drop in the CP. So in order to reshape the performance curve, we can look at the variables in terms of the blade geometry, so the pitch, the core distribution, and the twist distribution. And so what Katie Gracior has been doing is developing a methodology of how to do this. And this diagram here is showing sort of an example output from her methodology, which is designed to work with overspeed power regulation. So her model works firstly by specifying some design requirements. These are the ones specific to the example I just showed you, but you could change this around depending on what you wanted to do. This one, Katie chose to include a requirement that no cavitation would occur on the blades. So this graph here is just demonstrating she did quite a bit of analysis work to assess when cavitation would occur and design that out of the system. And then, so this is using an iterative process to optimize the blade geometry based on these design requirements using a blade element momentum theory code. And this graph here shows the output of this methodology. So again, for this example I just showed. So the dark blue are the initial design, and then the light blue are the optimized design. So you can see that we've got a much more rapid drop-off in the right-hand side of the power curve. But also what we haven't done is lost too much in the way of the peak CP, and we haven't got an increase in the peak thrust. So there's various ways you could do this, various different design requirements you could put into the methodology. You get different results output. But what this is showing you is that it is possible to successfully design blades that will operate with overspeed power regulation. So the second method for power regulation is then using bend twist coupled blades. So this is where you have flexible composite blades where the layup of the fibres within the composite mean that the blade increasingly bends with the increasing flow speed, and that induces increasing twist in the blade as well. Twist to feather, and hence reduces the power coefficient. So this work is being in partnership with Dalhousie University in Canada, and what they've done is developed a coupled blade element momentum theory FEM model, where they're using an iterative process to cycle through the outputs between the models until they get convergence, and this is under steady flow conditions. So what they're really looking at is the effect of the ply angle on the displacement and twist of the blade. Just to say, both of these control methods have also been sort of validated initially with experimental testing for the base cases, and then we've got upcoming in January a second set of tests where the final case study designs are then going to be tested experimentally to compare with the numerical modelling. Okay, well that's all I've got. I'll just say as well, Katie and Tom both have posters here today, so also if you do have any questions, please go and ask them. I'm sure they'd be happy to talk to you.
This production is brought to you by the University of Edinburgh.